Welcome, everyone. Let's get started. Today we are exploring a prompting technique that fundamentally changes how AI solves complex problems, chain of thought prompting. If you want Claude to handle advanced logic and math flawlessly, this is the training you need. Welcome to the concept of chain of thought, or COT. Normally, if you ask an AI a complex question, it tries to predict the final answer immediately. This is like trying to solve a complex calculus equation in your head without writing anything down. You are highly prone to errors. COT forces Claude to show its work. By generating the intermediate steps, Claude actually improves its own computational accuracy because each generated token of reasoning helps inform the next token. It moves the model from being a simple text predictor to a structured reasoning engine, while also giving you a transparent audit trail of how the conclusion was reached. Look at the difference in this flowchart. On the top path, a standard prompt forces the model to jump straight to the output, which carries a high risk of hallucination or error. On the bottom path, the chain of thought prompt routes the execution through intermediate reasoning nodes. The model extracts facts, analyzes patterns, and synthesizes data before arriving at the highly accurate final output. The simplest and most famous way to implement this technique is by literally adding the phrase, "think step by step," to your prompt. When you append these magic words, you are telling Claude not to rush. This prevents what we call first answer bias, where the model outputs a highly probable but logically flawed guess. Instead, you prompt, break the problem into smaller pieces. Solve each piece with explanation. Then combine the results. If Claude makes a mistake, you can read the steps and pinpoint exactly where the logic failed. It turns debugging from a guessing game into a precise science. This state diagram illustrates the pacing effect of the trigger phrase. Upon receiving input, the think step-by-step instruction immediately transitions the model into a decomposition state. Rather than rushing to the end, it systematically moves through solving part A, then part B, slowly eliminating variables. Only after these states are complete does it move to combine the results for the final output. It is crucial to understand how chain of thought fits into the modern AI landscape. Recent models, like Claude 3.7 Sonnet, feature native, adaptive thinking. The model dynamically decides to think deeply in a hidden block before giving you the answer. However, manual chain of thought via prompting is still incredibly valuable. You use manual COT when you need to force Claude to use a very specific, rigid reasoning framework rather than its default logic. It is also essential when you need a visible audit trail for compliance, allowing human reviewers to read exactly how the AI arrived at a specific conclusion. Here we see the processing routing. On the left, native adaptive thinking occurs internally represented by the dashed box and results in a clean output without showing the work. On the right, manual COT prompting forces the reasoning into the visible text stream. Both achieve high accuracy, but the manual approach gives you total visibility and control over the exact analytical framework the model uses. If Claude thinks out loud in plain text, your final output can get messy. The professional way to handle COT in production applications is by using XML tags. You instruct Claude, put your step-by-step reasoning inside thinking tags, and your final, user-facing result inside answer tags. This gives you the absolute best of both worlds. The model gets the accuracy boost of computing out loud, but your application can use simple regex like the sample code shown on the slide to strip away the thinking block. You deliver a perfectly clean, highly accurate answer to your end users while hiding the messy scratchpad calculation. This sequence diagram illustrates the XML extraction architecture perfectly. Claude generates the full payload containing both the thinking tags and the answer tags. Your application's parser intercepts this payload, strips away the thinking tags which were only there to help the model compute, and delivers just the clean answer content to the end user. The messy reasoning is completely hidden. Let's apply this to complex logic puzzles. AI models notoriously struggle with riddles that have multiple variables and constraints, like scheduling conflicts or resource allocation. If you ask for the answer directly, the model will guess and hallucinate. By using COT, you ask Claude to explicitly list all constraints first, then evaluate the options step by step. Because LLMs read sequentially, the text generation acts as external memory. The model writes down the state of the puzzle, allowing its attention mechanism to look back at the constraints it just wrote down before making the next logical deduction. You eliminate invalid options one by one until only the truth remains. Here is the logic puzzle workflow in action. We start by explicitly extracting the constraints into a list. Then we enter an evaluation loop. We test a hypothesis or option. The decision diamond asks, does it violate the written constraints? If yes, it is eliminated. If no, it is kept as a candidate. This rigorous loop continues until we reach a bulletproof final logical conclusion. Mathematics is the ultimate test for chain of thought. You must remember that Claude is fundamentally a language model predicting tokens. It is not a calculator. If you ask it to multiply large numbers or solve algebraic equations and jump straight to the answer, it will hallucinate. Code forces Claude to act like a diligent student showing their work. You tell it to break the formula down, solve the inner parentheses first, write down those intermediate values, and carry them forward. For maximum accuracy in mathematical tasks, you should explicitly ask Claude to self-check. Tell it, before providing the final answer, verify your math by working backward. This dramatically reduces arithmetic errors. This hierarchical tree maps the mathematical execution process. We don't jump to the answer. We decompose the formula into subparts. We compute subpart A and subpart B independently. We assemble those variables, and crucially, we hit the self-verification check. If the math checks out, we output the result. If an error is detected, the model catches its own mistake and loops back to recompute. Let's look at a real-time business use case, data analysis and verification. Imagine you hand Claude a large CSV file of sales data and ask for the main trends. If you use a basic prompt, Claude might scan the first few rows and hallucinate a trend that sounds plausible but isn't backed by the data. Instead, you use a structured Code prompt. Step 1. Describe the raw dataset. Step 2. Calculate the actual metrics step by step. Step 3. Summarize the insights based only on the metrics from Step 2. By forcing Claude to perform the mathematical observation before drawing the conclusion, you guarantee data integrity. You receive a highly accurate, transparent data report that business leaders can actually trust to make financial decisions. In this sequence diagram, notice how deliberate the process is. The user sends the Code prompt. Claude doesn't immediately respond. It first reads the schema from the data. Then it enters an internal loop where it explicitly computes the metrics, and only after those numbers are solid does it synthesize the insights. The final delivery is a verified trend report, completely eliminating the risk of data hallucination. To wrap up, chain of thought is your most powerful tool for accuracy, but you must be aware of its pitfalls. The biggest risk is error amplification. If Claude makes a logical error in Step 1, the Code process will amplify that error all the way down the chain. To prevent this, use Bootcamp Code. Provide 1 or 2 examples of correct step-by-step reasoning in your prompt to show Claude the exact analytical pattern you want it to follow. Also, remind Claude to keep its intermediate steps concise to save on token costs. Refactor your most complex prompts today using XML thinking tags and watch your AI accuracy skyrocket. Thank you for joining. I invite learners to like, subscribe, and visit quicktechie.com for premium certification prep, including massive Q&A banks, full ebooks, audiobooks, full-length training, and expert interview guides. See you there. Our final mind map summarizes everything you need for Code mastery. From the center root, you see your triggers, like the think step-by-step command. You see structure, utilizing XML tags to hide the messy work. You have your core applications in math, logic, and data analysis. And finally, your pitfalls to avoid, primarily error amplification and token bloat. Keep this mental model handy, and you will dramatically improve your AI workflows.